Welcome back to another episode of Dave Does Math from Home. This is part 2 of our series on Riemann sums. We are exploring the areas under curves by approximating that region with a number of rectangles, adding up the areas of all those rectangles. In our last video, we took the area under the curve y equals x squared plus 1 on the interval from 0 to 6. In the last video we split that into 3 subsections, so we were using 3 rectangles to approximate the area, and we got, honestly, a pretty terrible approximation. Our lower estimate was 46, our upper estimate was 118. When we averaged those, we got 82. And we're going to see if we can get a slightly more accurate approximation here by using 6 rectangles this time. And the process is pretty much exactly the same. If we split this interval into 6 sections, we're going to have 1, 2, 3, 4, 5, and 6. And we're going to make rectangles in here. We'll start with the lower estimate. These are the 6 rectangles we'll use for our lower estimate, or our left endpoint Riemann sum. So we're going to make a table of all these things. X is going to be 0, 1, 2, 3, 4, 5, and we're actually not going to use 6. 0, 1, 2, 3, 4, 5. These are our 6 rectangles. I don't need 6 right now. For each of these x values, again, the book calls these guys x0, x1, x2. Each of these things needs a height, which is going to be a y value. So the other way we could think of this is f of x sub I. So if you think of these different x values as x and an index, in this case I is for index, x index, the value of each of these things is just the function value. So this will be 1, 2, 5, 10, 17, and 26. Some of these numbers are familiar from the last time we did this. We had the 1 before, we had the 5 before, and we had the 17 before. So we're adding a couple numbers in between these guys. I am going to add another column for the width, even though all of these numbers are the same. They are all 1. The book calls this delta x. And then I multiply the heights and the widths to get the areas. So my area is 1, 2, 5, 10, 17, and 26. Multiplying the areas by 1, multiplying the heights by 1 it's always nice. It's always a good way to get these areas. And then I can get a left Riemann sum by adding these 6 areas together. So that'll be 3, 8, 18, 35. 35 plus 26 is probably 61. Okay, so the left endpoint Riemann sum, I usually just sort of abbreviate that to left Riemann sum, is 61, which is a lot closer to our 82 average than our first 46 guess. So left is 61. Now I'm going to do the right Riemann sum, which is going to use a lot of these same numbers here. We're just going to get an extra one at 6. And we're not going to use this first one at x equals 0. So I'm not going to use this one. I am going to use this one. 6 will give us 37 times 1 is 37. Not using this one, we're only using these for the right endpoints. We add those together and we will get 7, 17, 34, 60, 97. So our left is 61 and our right is 97, which is a much smaller range of values than our original 46 to 118 guess. That 46 to 118 guess was too big. It's still kind of too big, but it's a lot more reasonable. And if we average these two numbers, we'll get 100. The sum is 158, so the average should be 79. So we thought that the 82 sort of average from before was going to be a slight overestimate because this is concave up, which means that the straight lines that connect these things go above the function. And these straight line connections are what the average is giving us. It's essentially the trapezoid rule. So that our average estimate came down from 82, which we thought was a slight overestimate. This is good. This is promising. This is what we expected to happen. I think we can do even better. I'm going to do this again with 12 rectangles, and then we can look at some other problems and see what those are like. I'm going to draw this graph a little smaller because I feel like I'm going to need more room. We all know what's happening. X equals 0 over here, x equals 6 is over here. In between, I'm going to use 12 rectangles now, which means that these subintervals are going to have width of 1/2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, these are my rectangles. I'm also going to, for this one, I'm going to do the left and the right sums sort of together by just making a big table with all 13 of these endpoints. And then when I do the sum at the end, the left sum will be the first 12 and the right sum will be the last 12. So only the absolute far right side endpoint or the absolute far left side endpoint. Those are the only two things that would get excluded between the left and right Riemann sums. So we're just going to do the whole thing. 0, 1/2, 1, 1.5. Yeah, we're using decimals. Okay, 0.5, 2, 2.5, 3, 3.5, 4, 4.5, 5, 5.5, and 6. Just barely enough room. These are my x values. I need y values to be my heights. And half of these I already know. I know the height here will be 1. The height here, squaring 0.5 gives you 0.25. So this will be 1.25. This will be 2. This will be 3.25. This will be 5. This will be 7.25. This will be 10. This will be, I don't know, 3.5 squared. There'll be a 9 involved. Okay, let me get the calculator real quick for 3.5 squared. Apologies for the delay. 3.5 squared is 12.25. So this is going to be 13.25 when we add the 1. This is still going to be a 17. This one is 21.25. This is 26. This is 31.25. And this is 37. I probably should have just tried to find a pattern here, like 1 to 3 to 7 to 13, so plus 2, plus 4, plus 6, plus 8, plus 10. Probably would have been easier than going and getting a calculator, but here we are. So these are all my heights. Now I need widths. The width for all of these is 0.5. So I need to multiply these 12 heights by 0.5 to get my areas. So first area is going to be 0.5, then 0.625, then 1, then 1.625, then 2.5, then 3.625, then 5, then 6.625, then 8.5, then 10.625, then 13, then 15.625, and then 17.5. So these are the areas of my individual rectangles, all 13 of them. The first 12 of these will be the left Riemann sum, and the bottom 12, so everything except this top one, these will be the right. I'm not actually going to add these up because I don't have the calculator handy, and me going to get one is not going to be a very valuable use of our time. I will say, anytime I have to involve widths that are less than 1, I prefer to do these problems not just for the calculator, but with an Excel spreadsheet or with a Google Sheets spreadsheet. It turns out it's really easy to set up a spreadsheet that will do all of these calculations for you. So, for example, if you know that the width is going to be 0.5, all you really have to do is you can manually input the first x value. You can set up the second x value to be an equation that adds 0.5 to the above value, and then you can just copy and paste that equation all the way down until you get to 6. So that takes approximately 1.2 seconds. Finding these y values, you can again just input a formula that will take this value and do these things to it. And you can copy and paste that formula down to get all these numbers automatically generated for you. The width, you can just type in and then copy that down or fill down. And then the areas is just the product of two things. So you can do almost all of this automatically in a spreadsheet if you set that up. And the nice thing about doing this in a spreadsheet is that with a spreadsheet, it doesn't matter. Doing 12 of these on a spreadsheet is about as fast as doing 1,200 or 12,000. I could do this area approximation in 12,000 subsections. It would probably take me about 30 seconds on a spreadsheet because it's all just automated. You can make the computer do all of this work for you. The only thing that you actually have to do manually is figure out how far down you need to go in this list. So if you go down to the 12,000th row, and the computer will do all these calculations in microseconds. So that's the benefit of Riemann sums. And the benefit of doing this in 12,000 sections is you get very, very accurate answers. We saw in the first 2 sections we did, when we went from 3 subsections to 6 subsections, we saw how that dramatically improved our accuracy. If you did this with 12,000 subsections, you could get accuracy to probably the 10,000th place, or maybe just the 1,000th place. But you get extremely accurate values for this, and at some point it becomes essentially not really an approximation before. It's just, or not really an approximation anymore. It's just close enough to the exact answer that you're good. None of the homework problems in this section are going to ask you for exact answers. And honestly, I don't think any of them are going to ask you for this with more than 5 or 6 intervals. So the problems are going to look more like what we did at the start of this video than what we're doing now. I just want to show you that it can be done with more by hand without too much trouble, and it can be done with even more than this if you're feeling ambitious and have a spreadsheet handy. that's gonna about do it for these videos. I think I said earlier that we were going to do this with another function, but I think whatever function you use is honestly not very important. It just, whatever function this is, use that to get these y values. I don't, I don't think I need to do another one to illustrate that. Just get your y values, get your widths, multiply them, get areas, add them together. That's how we do Riemann sums. If any of the homework questions ask you for the midpoint rule, then instead of these x values that are the left or the right edges of your intervals, you have to find the x value that's in the middle. So now you know how to do that too. That'll do it for section 5.1. Thanks for watching. Next up is 5.2. We'll talk more about this.